Hello! Today we are going to see a bioeconomic model of parapenaeus, longirostris, and small pelagic species with mortality rates. Before to start, here is the plan that I will follow during this talk. First, I begin with an introduction. After that, I will introduce our biological model. Then, we will see the mathematical study of this model, namely the study of equilibrium points and their stabilities. Afterward, we will introduce the concept of catches made by fishermen in our model. Therefore, we get a bioeconomic model. And we will try to calculate the fishing effort which will allow fishermen to maximize their profit under the constraints of conserving the biodiversity of marine species. Next, I will give you some numerical simulation. At the end, I finish my talk with a small conclusion. The Moroccan coastline stretches for about 3,500 kilometers. Its waters are among the world's richest sources of fish. There are four fishing zones in Morocco: Mediterranean and North Atlantic zone to El Jadida, Zone A of Safi to Sidi Ifni, Zone B of Sidi Ifni to Cap Boujdour, and Zone C from Boujdour to Laguira, which allows the kingdom to be the first in the Arab world and in Africa for fishing for fish food and seafood, including small pelagic species and parapenaeus longirostris. It is found in abundance in the plateau and the Atlantic continental slope, from Cap Spartan in the north to Laguira in the south, and in the Moroccan Mediterranean from Ceuta to Saidia. Note that the parapenaeus longirostris undergoes migrations from Zone A to Zone B when they become adults. The parapenaeus longirostris is simply the pink shrimp. It is the favorite prey of the small pelagics: mackerel, anchovy, sardinella, horse mackerel, and sardine. The fishing of this creature has several advantages, both economically by being a source of foreign exchange and social by the labor it generates. However, shrimp fishing confronts several challenges and issues with regard to the nature of the resource itself and the context of exploitation. Overexploitation, especially of growth of juveniles of parapenaeus longirostris, remains one of the main causes causing the state of more or less advanced degradation of this resource. That is leading to significant shortfall for the fishery as a whole in terms of production per recruit and hence exploitable biomass. Our goal will be to protect the juveniles of parapenaeus longirostris against fishing. So, we consider the model of evolution of the biomass of the population of parapenaeus longirostris in the presence of predators in two zones: protected zone and unprotected zone. The first protected zone contains the juveniles of parapenaeus longirostris, and the unprotected zone contains the adults of parapenaeus longirostris. Then, we obtain a system of seven-ordinary differential equations. The first equation describes the natural growth of the juveniles of parapenaeus longirostris fish population, a prey of the small pelagic fish population. The second equation describes the natural growth of adults of parapenaeus longirostris fish population, a prey of small pelagic fish population. The third to seventh equation describe the natural growth of the small pelagic population as a predator of juveniles and adults of the parapenaeus longirostris. All parameters are mentioned below. When we solve the previous system, we obtain 128 equilibrium points. But the only point which gives the coexistence of all the species is the point x star, where all parameters are mentioned, with the conditions as below. When we study the stability of the point x star, we found that these points are locally asymptotically stable by using Routh-Hurwitz stability criterion. Note that all coefficients are written according to all parameters mentioned in the biological model. Now, let's calculate the catches made by fishermen in order to maximize their profit under the constraint of conserving the biodiversity of these species. We denote by each ij the catches of fish population j by the coastal trawler I, and it's given by H sub ij equal to qj multiplied by eij multiplied by xj, where q sub j is the catchability coefficient of fish population j, E sub ij is the fishing effort of the coastal trawler I to exploit the fish population j, and x sub j is the biomass of fish population j. By adding the catches formulate on the previous system, we obtain this new system, and the solution of this system is given by the matrix form x equal to minus ie plus x star. Now we go to profit calculation, and according to Gordon's economic theory, the profit is equal to total revenue minus the total cost. The total revenue is given by the formula, and the total cost is given by replacing each formula with its expression, we obtain then the final expression of profit as follows. As constraint of the bioeconomic model, we should have a strictly positive biomass of all the marine fish populations. In mathematical words, we must have the following inequality. To determine the mathematical expression of fishing effort that maximizes each coastal trawler profit, we use the generalist Nash equilibrium problem. By definition, a Nash equilibrium exists when no coastal trawler would take a different action as long as every other coastal trawler remains the same. This problem can be translated into mathematical problems of maximization. By applying the essential condition of Karush-Kontaker, this mathematical problem can be translated to a linear complementarity problem LCP. One can prove that this last problem has one and only one solution. So we can deduce that the generalist Nash equilibrium problem admits one and only one solution. Then this equilibrium solution is given by the system. For more details, you can consult my article, which will be cited in the references 1. Now, let's give some numerical simulation of the mathematical model and discussion of the results. We aim to study the effects of the mortality rate on juvenile adults of parapenaeus longirostris, as well as on fishing trips, profit and catches. As can be seen from figure 1, the mortality coefficient increase of small pelagic results in evolution in the stock of the parapenaeus longirostris population, which is justified by the absence of predators that feed on parapenaeus longirostris fish, and therefore the level of small pelagic population stock decrease as we see in figure 2. According to figure 3, the number of fishing trips that must be made by coastal trawlers to harvest parapenaeus longirostris increase. This increase enables them to make more catches, which allows them to get high economic returns taking into consideration the marine resources conservation. However, when the biomass of small pelagic fish decreases, the number of fishing trips dedicated to this species decreases because the carrying capacity of each small pelagic species doesn't contain enough biomass that allows the coastal trawler to catch a greater amount of fish. Note that each coastal trawler is constrained by the sustainability of marine species. In this situation, coastal trawler doesn't have the opportunity to catch more small pelagic fish, and as a result, their profit related to the exploitation of these resources decreases as shown in figure 4. If we consider the normal mortality rate assumed equal to 0.27, 0.19, 0.21, 0.17, 0.38, for sardine, anchovy, mackerel, horse, mackerel, sardinella respectively, in this case, the abundance of prey and predator stocks is ensured. Coastal trawler capture 819 tons and 552 tons of parapenaeus longirostris stock to have the maximum economic returns for small pelagics and for parapenaeus longirostris. We can notice that the total profit in this situation is the best situation. mortality rate on stock evolution of the prey population. Then we interpreted the best fishing situations which allowed sailors have the maximum income by preserving stocks of small pelagics and parapenaeus longirostris population. Thank you for your attention. Here are some references used in this work. For more detail, you can consult my article number 1.